Hello everyone. Today I'm gonna talk about the QSYM, a practical concolic execution engine tailored for hybrid fuzzing. This is joint work with my colleague Sang-Oh Lee, Meng Su, and Professor Tess Kim from Georgia Tech, and Professor Youngjin Zhang from Oregon State University. As you might know, there are two popular ways to find security bugs, fuzzing and concolic execution. Those two techniques have their own pros and cons. First, fuzzing, which randomly generates the input. It is good for finding some general inputs, but it is bad at finding some specific inputs which are highly constrained. And concolic execution is good for finding such kinds of input, but it has a fundamental problem called state explosion. Hybrid fuzzing can address this issue by combining these two techniques. It can find those kinds of specific inputs using concolic execution, and it can limit state explosion by limiting forking at only the branches which are hard for fuzzing. Hybrid fuzzing has achieved great success in small-scale study. For example, the driller, which is one of the state-of-the-art hybrid fuzzing, it won the third place in CGC competition, which is the competition that makes the automatic system for finding bugs and exploitation. It found 6 new crashes from the CGC competition, which cannot be found by neither fuzzing nor the concolic execution. However, if we apply this current hybrid fuzzing, it suffers from many problems to scale to real-world software. First, it is very slow to generate constraints. And second, it cannot support complete system call, which is essential for supporting the real-world software. And third, it is not effective in generating test cases. So our system QSYM can address this issue by introducing several key ideas. First, we discard intermediate layer, which is one of the performance bottleneck in current concolic execution for hybrid fuzzing. And second, we use concrete environment to support system calls. And third, we introduce several heuristics to efficiently generate test cases for hybrid fuzzing. QSYM is really scaled to the real-world software. We found 13 previous known bugs in open source software. And we want to note that all applications are already fuzzed by AFL or OSS fuzz. The bug that we found, including the bug in FFmpeg pack, which is being fuzzed by the OSS fuzz for more than 2 years. And these bugs are hard to find by fuzzing because it requires some complex constraint to find these bugs. So before we jump to the QSYM, I want to introduce hybrid fuzzing in general. So in the program, it extracts a basic block and it converts its basic block into the intermediate representations for simplicity. After it generates the intermediate representations, while executing intermediate representation, it generates constraints and it also forking some states. Unlike classical concolic execution, when it forks, it gets the information from the fuzzing for the code coverage and decide whether it wants to forking or not. And after it gets the constraint, it solves this constraint using constraint solver, and it generates test cases and feed these test cases back to the fuzzing. There are several problems in this design. First one is that the intermediate representation. Intermediate representation currently introduces significant performance overhead that slow down this hybrid fuzzing a lot. To mitigate this, QSYM directly generates constraint instead of using the intermediate representation and remove this layer. And the second is state forking. State forking introduces several problems in the environment modeling. So therefore, instead of forking, we use the concrete environment modeling to support complete system calls. And third, when we generate the test cases from the constraints, there is inefficiency come from the unsatisfiable paths. So QSYM currently optimistically solve this constraint to generate useful test cases for fuzzing. And finally, this constraint generation can be blocked by some complex logics like a compression or decompression or the encryption or decryption. QSYM uses page block pruning to handle this issue, but due to the time limit, in this presentation, I will not cover this, so please refer our paper for detail. So first, I would like to talk about the performance overhead introduced by these intermediate representations. So people use intermediate representation because they are good to make implementation easier. So it provides the architecture-independent abstraction, and we can reuse code for all architectures. For example, Anger, it works on many architectures, including x86, ARM, and MIPS. But IR incurs significant performance overhead. First, the reason is that it increased the number of instructions. In our evaluation, the FAX, which is the IR used by Anger, it increased the number of instructions by 4.7 times. And we need to execute a whole page block symbolically. The reason is that because of the caching and optimization when generating this intermediate representation. But the problem is that only 30% of these instructions need to be executed symbolically. So we need to execute 70% more instruction which do not have to be executed symbolically. So solution for that, QSYM execute the instructions directly without using this intermediate layer. Yes, we have to pay this implementation complexity, but we are willing to pay this implementation complexity for our performance. As a result, QSYM reduces the number of instructions a lot. We tested QSYM and Driller, which is one of the state-of-art hybrid fuzzer in 126 CGC binaries. QSYM needs to execute 4 times less instructions than Driller. Second one is that the incomplete environment modeling due to the state forking. State forking is good because it can reduce the re-execution overhead for constraint generation. So if you want to reach some state, you don't have to re-execute. You can just recover from the snapshot. But the problem is that this state forking is non-trivial. So state in concolic execution can be divided into two, program state and kernel state. Forking program state is trivial. You can save memory, register, and constraints. But forking kernel state is non-trivial because you need to maintain all the kernel data structures such as file system, network state, and memory system, and those kinds of things. So to handle those, there are two main ways to handle this state forking in kernel, but they have problems in either completeness or performance. For example, kernel modeling, which is used by Anger, it models the kernel functions. It provides the small performance overhead, but the problem is that it causes incompleteness. Currently, Anger can support only a limited number of system calls in Linux. Second one is full kernel emulation, like used in S2E. It treats kernel as a program, so it provides a completeness. But since we need to execute kernel symbolically, so it introduces a large performance overhead. So to resolve this issue, we use the re-execution instead of state forking. We know it will introduce the high re-execution overhead, but we can reduce this high re-execution overhead by using instruction level execution and the basic block pruning. And we also can limit the constraint solving because we are in a hybrid fuzzing, so we can limit the constraint solving based on the coverage information from fuzzing. So QSYM only models minimal system calls related to the user interactions. For example, the standard input or file read or network interface. And if there are other system calls, then we call system call using the concrete values. So for example, if we have mprotect with the symbolic size, then we converted it to concrete size and call this function. The problem of this concrete environment is that it can result in some incomplete constraints. For example, if we convert this mprotect with the symbolic size to the concrete size, then it will add some implicit constraint. So without knowing the semantic of this system calls, then we have only two choices. First, concretize this value, which results in the over constraint, or we just ignore this value, and we will suffer from the under constraint problem. To resolve this issue, QSYM uses unrelated constraint elimination, which is the classical optimization for constraint solving. This unrelated constraint elimination only solves the constraint related to the branch. So for example, there is a sample program which gets x and y as an input, and it calls mprotect with x, which results in the incomplete constraint for x. And if we hit the last branch, then the path constraint will be the constraints for x and the constraint for y. In that case, constraint for x is incomplete, but if we extract only the branch-dependent constraint, then the constraint will be the constraint only related to y. And we solve this constraint using the constraint solver, and we use the x as a concrete value. By doing so, we can tolerate incomplete constraints. Third, I want to talk about ineffective test case generation due to the unsatisfiable paths. Another problem is that it may be over-constrained paths and it results in no test cases. For example, there is another sample that it gets type, and it checks whether type is type 1, and after long execution, it will check type equal to type 2. If we first go to the type equal type 1, and after the long execution, then even though we meet the type equal type 2, it will not generate any test cases, definitely because it is unsatisfiable path. Because the type cannot be type 1 and type 2 at the same time. But if these branches are independent, then there must be the path that the type is not equal to type 1 and the type equal to type 2. And in that case, we will generate the type 2. But it requires another long execution, go back to first branch. To resolve this issue, what we are trying to do is that we want to solve constraint optimistically. More specifically, we want to solve some part of the constraints instead of giving up at the unsatisfiable paths. So our decision is that we solve only the last constraint in the path. It is simple because it is only one constraint at the last branch. And it is highly likely to pass the branch because it meets the condition for the last branch. If we are wrong, we will waste only a small solving time. And also in hybrid fuzzing, generating incorrect inputs are fine. Because even though we generate the incorrect inputs, it will feed back to the fuzzing, and the fuzzing will filter out these incorrect inputs. So we can generate the incorrect inputs. This optimistic solving really helps to find more bugs. This is the result from the LavaM dataset, which injects some hard-to-find bugs in real-world software. X-axis is time elapsed for testing. We run the QSYM for 5 hours. And the Y-axis is related to the number of bugs found by the QSYM. So you can see the blue line, which is the QSYM with optimistic solving, is dominate the red line, which is the QSYM without optimistic solving. So optimistic solving really helps to find more bugs. Implementation, we implemented the QSYM with 16K lines of code. We use Intel Pin as our emulation, and we use Z3 for constraint solving. So you can, we will open source our prototype, so it will be available at this link. So please check this link. So for the evaluation questions, we want to answer our goal is to scale to real-world software. QSYM really scale to real-world software. The second one is that we want to compare our QSYM to other systems like a driller, one of the state-of-the-art hybrid fuzzing, and Fuzzing, and the other fuzzing and symbolic execution techniques. QSYM scales to real-world software. We found 13 bugs in real-world software, including Lepton, OpenJPEG, TCP dump file, and FFmpeg and object dump. As you can see, they are already fuzzed a lot, and there are some programs that are being fuzzed by the OSS Fuzz, which is the cloud fuzz from Google. Even they are already fuzzed, QSYM help them to find the bugs in this program. One example that we found bug in the FFmpeg, it requires to pass these very complicated branches. In our evaluation, we run the fuzzing for 24 hours, but it cannot reach this branch at all. And we believe it's really hard for fuzzing because OSS fuzz this program for 2 years, but it cannot reach this bug. But QSYM can generate the test cases that bypass this branch, and we found this bug using QSYM. And we compare QSYM with driller. We use the data set from the CGC, 126 binaries. And we run only one instance of concolic execution for 5 minutes, because we do not want to run the fuzzing because it will introduce the randomness in our experiment. After running the concolic execution for 5 minutes, and we compare code coverage of the generated test cases. And QSYM achieved more code coverage than the driller in most of cases in CGC. Among 126 challenges, QSYM achieved more in 104 challenges, and the driller achieved more in 18 challenges. QSYM achieved more code coverage due to its better performance. For example, there is a challenge named Chromu1. To achieve new code coverage, it requires 7 stages. It needs to add user, and it needs to add another user, and the login and send message, and require 7 stages for that. QSYM can reach this state and can find the new code coverage, but driller cannot do in time. But driller can achieve more code coverage if there is a nested branch. Driller can find inputs that pass the nested branch by a single execution due to forking. So if there are the nested branch, QSYM only flip one branch, but driller can follow the branch and can generate test cases to pass this nested branch. To do that, QSYM requires re-execution, but we want to note that our experiment allows only one instance of concolic execution. So we believe that the QSYM can reach this state by doing the re-execution. And the QSYM outperforms other techniques in LavaM dataset. As I mentioned before, LavaM dataset inject hard-to-find bugs in real-world software. We run 5 hours, and QSYM found all the bugs in unique, base64, and the MD5 sum. And it found 58% of bugs in Who, which is significantly more than other techniques, fuzzing and symbolic execution and fuzzer. In this slide, I want to discuss the other use of our technique and the limitation. So the QSYM is based on the less accurate result. So it requires efficient validator. In our case, fuzzing is efficient validator. Maybe we could apply the same technique on the exploit generation because we can make efficient validator to test whether the generated exploit works or not. Currently, we only support x86 and x86-64, and we cannot support floating point yet. Conclusion, I want to conclude this talk. QSYM is a hybrid fuzzing scalable to real-world software. We found 13 bugs in real-world software, and we outperform a state-of-art hybrid fuzzing and the other bug finding technique. So please, we will open source our prototype, so please check this link. Thank you.
We have time for a couple of quick questions. Run.
Hi, Sumanjana, Columbia University. Cool work. So I just have one question for the real-world programs that you tested. Did you test for coverage as well? Because you talked about bugs, right? You found 13 new bugs. Did you compare coverage with other hybrid fuzzers on real-world program?
So honestly speaking, the only hybrid fuzzer we know the driller, and the driller has some a very high dependency on the CGC program. So we try to test a driller with the other ERF like a normal Linux binaries, but we failed. So we only actually it generates some test cases, but they are too small to generate. So we think it's not that meaningful to compare those, so that's why we compare the driller with CGC binaries.
Okay, and fuzzer, did you compare fuzzer or not?
Fuzzer?
Fuzzer, V-U-Z-Z-E-R.
Oh yeah, so we just compared their evaluation in the LavaM dataset. So we use the LavaM dataset. Not
the real-world programs, right?
Not the real-world programs.
But it runs on the real-world programs, right?
Sorry?
It does run on real-world programs. Like you're basically saying,
yeah. I think we haven't tested Visual with the real-world program, but I definitely sure it will work with.
Okay, cool. Thank you.
Thank you.
Let's thank our speaker again.